is the first of a planned, thank you, series of climate-related webinars that Terrain's going to deliver as part of our new climate focus. So these webinars are our way of trying to increase our own knowledge and that of our community, and working to support united climate action across the region. So we're really lucky to start this series off with Professor Steve Turton, who, as many of you already know, has a depth of knowledge of climate impacts in the wet tropics, which he's going to share with us today, along with his update on the IPCC report that was just presented a couple of days ago. So welcome, Steve, and thank you for agreeing to present this webinar today.
Yeah, thank you, Sarah, and it's great to see so many faces and names there. So I'd also like to acknowledge the Cubby Cubby and Jinnabara people of the Sunshine Coast, from where I'm presenting from today, and pay my respects to elders past, present and emerging, and also acknowledge the many traditional owner groups of the Wet Tropics region as well. Yeah, so when I moved down here, I thought I was getting away from the Wet Tropics, but it looks like all the rain has followed me to southeast Queensland, but that's just what happens, I guess. Maybe it's all part of climate change. So I'd like to begin by, I guess, just referring to the two IPCC reports that I'll be referring to in my presentation. The 2021 report, most of us who've looked at that have had a lot of time to digest it because it came out in August last year. And that's probably the most of my focus today. The other report only came out on Monday, although I've actually had access to Working Group 2 throughout the writing process as an expert reviewer. So I've been able to read the chapters in their earlier forms, which has been useful for me, particularly seeing I'm writing a book on climate change at the moment. But that focuses more on adaptation and vulnerability, which I'll only touch on today, but I'll be talking to Elaine and Sarah about possibly giving another webinar where I'll focus a bit more on impacts and adaptation for the wet tropics. So today is a bit more on the science side of things, with a touch of, I'll touch briefly on adaptation and vulnerability, mainly vulnerability though. So if you haven't read these turgid reports, they should be essential bedtime reading, guaranteed to cure insomnia. However, if you don't want to read the technical reports or the individual chapters, you can go straight to the summary for policymakers, which they're very, very useful for giving you that nice overview of the science without having to get into the nitty-gritty of the detail. They are written for policymakers and those sorts of people, decision makers and everyday people. All right, so I think I'll just start off by just setting a bit of context around this idea that our climate has always been variable, but now it's actually changing. And for many people, that's probably not something that's too difficult to understand. We know we've had past climate change going right back to the evolution of the planet. We also know that in the last million years, we've had a lot of change, a lot of cycles between glacial and interglacial cycles, and sea levels varied by over 100 meters during that time. That's significant global change. But of course, the rates of change were at the kind of millennial scale, sometimes centennial, but mostly multi-millennial scale. But now we're talking about change occurring at the decadal scale, so the scale of a human lifespan. So it's a very different rate of change compared to what we've seen previously. There have been times, of course, when significant events have occurred, like when an asteroid hit the Earth 65 million years ago, and that would have been rapid climate change at that point, well before humans even evolved on the planet. So those kinds of events have occurred in the past, but they have been remarkably rare, thank God. So let's bring us into where we are now. We've been thinking about the last 12,000 years when we came out of the last interglacial maximum. We had the rising of sea level stabilizing around 9,000 years ago or so. And this period is known in the geological record as the Holocene epoch. And we were probably, when we went to school, we were told that we were living in the Holocene. And no one would have thought that when we grew up and became adults, we would be told that we're now living in the Anthropocene. The Geological Union formally recognised that sometime in the distant future, there will be a layer in the geological record of the human imprint on Earth's geology. I don't know what it'll look like. It'll be pretty interesting, I'm sure. Hopefully it doesn't have a lot of nuclear material in it, but who knows? So as to when the Anthropocene began, well, people have been debating that for some time, but most people say it's something that occurred around the late 1950s, when we start to see a very distinct human imprint, not only on the climate system, but on the biosphere, all the different sort of components of the Earth system, and also the atmosphere and the oceans and so on. And it's not just about climate, it includes chemical tracing, all sorts of things like that. So I won't go into the Anthropocene too much detail, except to say we're living in it. So if you go back over the last 12,000 years or so, when human populations have grown and there's been civilization has flourished here and there, it's also failed here and there as well as because of climate. You've got this long sort of period of stationary climate, but it's highly variable. So you've got this patterns going up and down. Now, this could be temperature, it could be rainfall, it doesn't really matter, it's just a schematic. But let's just assume it's just temperature. So what it shows is that, yes, there's high variability from year to year. That's normal background variability, which I'll talk about in a moment. But for the most part, civilizations, ecosystems, and the like of all, and agricultural systems as well, have all resided or lived within their coping range. Occasionally, we've left the coping range. This could have been an extremely hot year, or extremely dry year, or extremely wet year, whatever. But most of the time, we've had this recovery. And if we fitted a running mean to this data set, we would actually get a flat line. So we have a stationary but variable climate, all right? Come the Anthropocene, we're now starting to see a distinct human fingerprint, if you like, on the climate system. And we still have variability from year to year. That's not going to go away. That's part of background variability. But if you look at this data set, if you go from this point onwards, you can see an upward trend in this particular climate attribute that's being plotted here, which we might think of as being temperature. And you can see that if you fitted a sort of a running mean to this data set, you would, what's happened? You would have an upward trend in the data, showing no longer a stationary climate, but a changing climate. And of course, if you start moving out of this coping range, you have to be thinking about adaptation. And that's really what that Working Group 2 report is all about, the one that came out on Monday. And then, of course, once you start exceeding your adaptation sort of space, you're moving into vulnerability. So this is kind of where we are now. We're not quite in 1950. We've moved along a little bit, but this is the planning horizon that we have to be thinking about going into this century and beyond. So if we look back over time, we kind of definitely are living in uncharted territory. Unfortunately, I didn't move the set. The subtopic's cut off some of this data here. You can see that going back 800,000 years from today, so this is where we are today, or zero, you can see the carbon dioxide levels in the Vostok ice core down in Antarctica give us a really nice record of past levels of carbon dioxide, methane, and nitrous oxides. And they go up and down with the glacial cycle. So here's the peak of the last glaciation, when they got down to about 160 to 180 parts per million. Some people say vegetation might have been choking then because it would have had to work harder, the stomata in the leaves, but it was also cooler, so there was less pressure, I guess, on the stomata to function. And this is the last interglacial 125,000 years ago that definitely was warmer than the current interglacial before the Anthropocene, before we started having an imprint on the climate system. And that got up to about 290 parts per million. There's one back here, though, that got up to, approaching 300 parts per million. But if you go right back through that record, it's never been higher than about 290 parts per million in that record. Now, since the late 1950s, a fellow by the name of Dr. David Keeling, he passed away only about 7 years ago. He decided to set up a monitoring program on Mauna Loa in Hawaii, on the observatory up on the volcano on the big island of Hawaii. And this is known as the Keeling curve. And he was a very meticulous scientist. And you can see that this shows the pattern of nature, the up and down signal every year from the deciduous forests in the Northern Hemisphere that suck up CO2 and then release it. That's a natural cycle. But you can also see the escalation of CO2, particularly since the year 2000. This curve's gone up. And this is where we are now. It's currently 416 parts per million as of this month. So we know that we're living in uncharted territory, way higher than anything we've ever seen for at least 800,000 years. And some people are saying from other data sets, possibly going back even to 20 million years or so. So what drives this background variability? What causes us to have natural variability in climate? And we have a series of drivers. We've got this internal variability. And the main driver of this is the El Nino, La Nina cycles that we go through every 3 to 7 years in the Pacific Ocean. Pacific takes up so much of the Earth's area, such a vast ocean, that it affects the whole Earth climate system. So when we have what we might think of here as being a El Nino, we've got warm water in the Eastern Pacific and cooler water over Northern Australia. We get this warm water off the coast of South America, cuts off the upwelling of cold water. Normally the upwelling cold water acts as a giant air conditioner for the planet. And you get below average temperatures during La Ninas. But when you have an El Nino, you cut off the air conditioner and you get above average years. So you can be certain that every La Nina globally, it's cooler than the long-term average. With an El Nino, it's warmer than average. And the stronger the El Nino, the greater it is above average. And likewise, the stronger the La Nina, the greater it is below average. And then most years, which make up 70% of years, called neutral years, and they have average global temperatures. So don't rule out the importance of the internal variability driven by El Nino, La Nina, or ENSO cycles. We also have some what are called external forcing mechanisms. They're external because they're coming from, it's different to internal, which is a process is to do with the sloshing backwards and forwards across the Pacific. There's external forcing mechanisms. Some of them are random or spontaneous, like volcanic eruptions. And the last big volcanic eruption was Mount Pinatubo in 1991 in the Philippines. And this was such a big eruption that it led global temperatures fell by about up to ½ degree below average for 2 or 3 years after the eruption. It also had a lot of sulfide particles in it that were highly reflective to incoming solar radiation. So that sunlight was reflected out to space, so that led to global cooling. It's interesting that the latest eruption very big eruption, second only to this one, near Tonga, does not appear to have been a high sulfide eruption. At this stage, although we've had lovely sunsets and everything, it doesn't appear to have had any impact on global temperatures compared to anything like Pinatubo. We'll wait to see what the data is because it's still early days for that. The sun, of course, has variability in its output as well. You might have heard of sunspot cycles. This is what's shown in the graph on the right here. This dashed line here are the classic 11-year sunspot cycles. We've known about those for some time, ever since people have been studying the sun. This is the 11-year running mean in the bold line. So if you look at the sun between 1880 and where we are now, you can see it peaked mid-century, sort of 1940s, early 60s. And it's been at a gradual decline ever since. And in fact, we are now moving into a solar minimum, a period of lower sunspot activity. So the sun actually is giving us a bit of a free ride at the moment because it's having no effect actually on global temperatures. They continue to go up. However, if we were in a higher sunspot cycle, we'd be looking at faster rates of global temperatures. So there's a bit of a free ride there, but we can't rely on the sun to overcome the impacts of rising greenhouse gases. And that's what this diagram is showing you here. Fuels make up most of our greenhouse gases, 40 to 50%, depending on the country, are coming from fossil fuel emissions. Another driver of climate change is, of course, land use change. This is a satellite image just showing where you had changes in land use. This could be deforestation, reforestation. And obviously when we think of images like this, we tend to think of the Amazon basin. Some of Bill Lawrence's work where there's been widespread clearing of rainforest and replacement with fields of soybean and grazing. You actually change the microclimate, and that has a big impact on the larger scale climate. So that's another thing to think about. It's called land use change. Okay, so where are we in terms of the latest IPCC report? What it does show is we've got these changes in global temperatures, and the diagram on the left is just a reconstruction of the last 2,000 years. And this is relative to 1850 to 2020. So this is reconstructed. It's mostly reconstructed from tree ring data, other kinds of data collected at the bottom of, from sediment records in the bottom of lakes and so on. And that allows researchers who specialize in this paleoclimatology to reconstruct the climate system, global climate system. You can see that from about 2,000 years ago to about 1,000 years ago, so from, if you like, time of the Roman Empire through to about getting into the Middle Ages, the climate was very stable. It only had that natural variability that I was talking about, but was remarkably stable. And then we find that prior to the Industrial Revolution in 1850, we've actually had a slight decline in temperatures. And the main driver behind this is likely to have been increased volcanic activity in that second millennium. And some people have done analyses and found that there were 4 times many eruptions between 1,000 years ago through to 1850 than there was in the previous 1,000 years. So that appears to be a driver. Also, there were periods of lower solar activity. We had a solar minimum as well, known as the Maunder minimum. And some parts of the world experienced a little ice age at that time, from about 1450 through to about 1850. And that seems to have been driven by natural processes, not human processes. However, let's have a look at where we are now. We're here. So we've exceeded, we're about 1.1 on global average, 1.1 above the 1850 to 2020 average. And that's unprecedented in 2,000 years. And when we compare that with the warmest multi-century period in more than 100,000 years, again, this is all reconstructed from paleo data, you can see that we've exceeded that as well. So we're really definitely in uncharted territory. The next one on the right just looks at what's happened since 1850 through to 2020. This is a global data set. Now, what you can do in climate work is it's a technique called hindcasting. And hindcasting is something that they do when they try to work out river heights in hydrology, for example, and they want to run a model to see how good that model is. They hindcast it or run it back in time, and then they compare it with the real data from the flood event. And that means next time there's a flood event, hopefully they can better predict it. So that's what's shown here is, this is the black line here is the actual observed climate data. And you can see here it goes up and down with that natural variability. This is the Mount Pinatubo eruption here, where I'm pointing. And this is the big 1998 El Nino, which at that time was completely off scale to anything we had seen in hundreds of years. Now it's dwarfed by the temperatures that we're getting today, even during La Nina years. So what used to be a standout is now considered just to be quite a minor event. Just goes to show how things have accelerated in the last 20 years. The orange line, though, is a simulation, a hindcasting model. And you can see the orange line and the black line, look, they're not perfect, but they actually have about a 95% agreement, which is pretty good. You can see that the model has overpredicted the volcanic eruption from Mount Pinatubo. Nonetheless, there's a pretty good fit. Both of them are actually showing the right patterns. You can also see that up until about 1950, there's a lot of noise in the signal. There's not really any discernible trend. It's pretty flat. It's really only when we get to the 1970s that we're starting to see a distinct human trend affecting the climate. And this one way to look at this is just to look at only the simulated natural, which is solar and volcanic, to remove the effect of greenhouse gases added by human activity and also land use change. And what this shows is that we should have actually cooled slightly globally from the 1950s, because we had a lot of volcanic eruptions in the second half of the 20th century. It's been fairly quiet this century so far. We have Pinatubo here. We've got, this is Agung in Bali, 1963. So we've got a series of quite big events that put a lot of ash into the atmosphere. But for the most part, there should have been general cooling because, as I pointed out before, we've had a reduction in solar activity as well. But the reality is that we're tracking up here. So the difference between this curve and that curve is really, this is the human imprint on the climate system. And the gap is getting wider every decade. And you can project this out into the future. Yes, there'll be future volcanic eruptions. Yes, the sun will wake up again, probably around 2040. But for the most part, we have got a much stronger human imprint now on the system. We can really see what's happening in the oceans. We live in the atmosphere. We're not a marine animal. But, we think about it, the oceans make up 71% of the surface of the Earth, all right, something like that. And at the moment, they're taking up 90% of the excess energy that's been accumulating in the atmosphere. This is data between 1971 and 2019. So the atmosphere is really only like a thin veneer around the surface of the Earth. The oceans are deep. They have a ability to absorb heat and retain heat. So this is ocean heat content, and it just goes, it's pretty fuzzy up until about up to about 2000. And then with better measurements from satellites, but also instruments at different depths out in the ocean, you can see that it's taking off very, very rapidly. We're getting this massive uptake of heat. And I do have a figure somewhere, but I think it's one and a half Hiroshima bombs per second is the excess energy going into the oceans in terms of an energy component every second of every day, something like that. We look at the world as a whole, and this data here is just showing you what's called a temperature anomaly. So when you're below the zero line, you have a negative anomaly with regard to the 1961 to 1990 baseline. So when you look at data sets, sometimes it's 1971 to 2000. This particular data set from the World Meteorological Organization is 1961 to 1990. It doesn't matter what baseline you use. All you do is just change the trouble with my mouse, you just change the zero intercept. You don't change the patterns in the data at all. So if we look at that baseline, we can see that, this gives you some idea of, maybe our parents or grandparents. This is the world they were growing up in, where, you've got these negative anomalies with regard to the baseline. All the La Niñas were cooler than average, as they should be. Even the odd El Nino. But for the most part, once we move into the later part of the 20th century, we find that even La Niñas are warmer than the long-term baseline. In fact, there are no La Niñas since 1990 that have actually been cooler than the baseline, including the one that we went through in 2021, which was about 0.4 of a degree. It's not shown here, it has been updated. So you can imagine the 2021 La Nina was about 0.4 warmer. And we're currently in the La Nina at the moment. Well, it's only February, so it's too early to tell. You can also see that the 2016 El Nino, this is what caused the massive bleaching on the Great Barrier Reef, the northern part of the Great Barrier Reef, and also that loss of mangrove in the Gulf of Carpentaria. You can see that, as you'd expect, we had a real spike. Now we go back to 1998, which at the time we thought was just You can imagine not having the data on the right here, how it stood out like a sore thumb. Well, now you look at it and it's quite puny, isn't it? So if you look at the warmest 10 years, you'll find they've occurred, all of them have occurred in this decade, except for this one, 1998. So all of the warmest years have occurred this decade, and that includes neutral years, which are the light blue colour. We've yet to see a very warm La Nina. This one, though, was, look, it's warmer than some of the El Ninos of the past. So it's a very different sort of climate that we're living in today, and we've not really had a lot of volcanic activity since that Pinatubo events. And again, they tend to be random, but it's important that we document when these events occur, because we know that they are a driver of climate as well as rising greenhouse gases. If we just have another look at how Australia has been tracking, we basically are following the global trends. So this is just another way of looking at that data I showed you. You've got negative anomalies, positive anomalies, same baseline. And you can see that the orange line is the surface air temperature and the blue line is the oceans, the sea temperatures around Australia. This is a composite data set, and you'd expect the land to show more variability from year to year because the atmosphere behaves differently to the oceans. The oceans have a much smaller frequency, if you like, between years, but nonetheless, they do vary as well. Again, because of El Ninos, La Ninas are the main drivers there. So you can see we've not really, we're just getting warm years pretty well. Every year has been above average baseline since about 1980. Just slightly dipped down here on that 1 year. Having a look at sort of what's happening with global sea level. Sea levels around Australia more or less are following global trends, but they do vary. So the southeast of Australia, so sort of from Brisbane, Gold Coast, right down to the Victorian border, that has had a higher change in sea level than other parts of Australia. So you do get variability in sea level change, even though it's kind of hard to comprehend because you think water always meets its surface, but it doesn't quite work that way because of currents and also because of the Earth's rotational force. And again, all of this is explained in the IPCC report. There's a whole section just on sea level change, very complicated. Let's have a look at rainfall deciles. So this is just showing that the top diagram is focusing on the northern wet season. So this is kind of your November to April. And what it is showing is generally above average, particularly, not even parts of the wet tropics north of about Ingham, but also right across northern Australia. With the last 2 decades have been wetter than average. So they're still trying to figure out what's driving that. This is not dry season rainfall, this is wet season rainfall. But what it is also showing is that the southwest of Western Australia, which normally has its Mediterranean dry season anyway in the summer, is getting drier even then. So is the west coast of Tasmania. This is probably more alarming because Western Tasmania is not a Mediterranean climate. It is a seasonal climate. It gets rain all year round, which is important for their hydroelectricity, for example. So this is not a good thing to see this big drop in summer rainfall in Western Tasmania. And likewise in this part of Victoria as well. A lot of this is around the dams that are important for Melbourne water supply. I guess what's more grim is when we go to what is our dry season, or April to October rainfall, which is the southern winter, autumn, spring wet season. So in southern Australia, gets most of its rain. That's important for its agriculture, for example, and its water supply. You can see this horrendous drying in the southwest of Western Australia over massive areas, lowest on record over the last 2 decades. No one knows what's driving this extra wetting in Tasmania. So maybe it's making up for the shortfall that's not happening in the summer. But you can see that pretty well from, the Hervey Bay area, maybe Bundaberg, right through that we've had the significant drying trends. In some cases, it's been the lowest on record. So what we're seeing is effectively a climate change signal that is affecting rainfall in southern Australia in what is normally its wet season, which is the winter rain and spring rain, and that's also occurring in southeast Australia as well. Kind of what's happening in the north, this is normally the northern dry season anyway, with the exception of the wet tropics that gets rain all year round. All of these areas are savanna climate, but you can see that they seem to be getting a little extra bit of rain. But they're starting from a very low baseline. When we look at sea surface temperature, what we find that's very interesting is got the significant warming in this part of Australia, and this appears to be driven by the strengthening of the East Australia Current. So the East Australia Current is strengthening and it's moving further south. This is bad news for the fisheries in this part of Australia that depend on the upwelling of cooler water and nutrients. They don't really want that tropical water coming down and affecting those fisheries, and having a whole bunch of other knock-on effects for ecosystems like kelp forests, for example, and deoxygenating the water as well. So that is a pretty strong signal that we're seeing. The rest of Australia, the trends, they are warming, but the significant warming is this southeast section right down into northern Tasmania. The acidity of water, this is important when we think about the Great Barrier Reef. Any kind of ecosystem that is calcium has a lot of calcium-based life forms. And we think about pH, we have to remember it's a logarithmic scale. And you can see that we're getting this acidification of the waters around Australia that is following global trends. So that excess carbon dioxide is being dissolved into the oceans and in the form of carbonic acid and making the oceans more acid. But also deoxygenation, which I'm not showing you here, but it's in the IPCC report, has also increased, and it's the highest rates of deoxygenation have been in tropical and subtropical waters. Heat waves. Okay, so sometimes, great grandma says, oh, we used to have heat waves in the old days that were far worse than now. And this is why you can't rely on human thermometers. They're not very reliable. You need to rely on real thermometers. And, that's why we need these kind of data sets. You can see, though, that we're getting a lot more heat wave events now as the world warms and we shift the baseline. We're getting less cold waves and cold spells. We're getting more heat waves. This is a pretty strong signal there, especially since about the 1980s. This is transpiring across to this diagram on the left here, showing us the number of dangerous fire weather days in Australia. And you can see that there's generally been, red just means dark areas mean there's been an increase in the fire weather index. And Northern Australia is not immune from this. It's just that obviously the burning seasons are different. They're mainly in the winter months. But you can see there's been a big area here through southeast Queensland into central Queensland. Pretty well the whole country, with few exceptions, has had an increase in the number of dangerous fire weather days. And I guess the 2019-20 Black Summer it sort of stands out there for its severity and extent. Now, when we go into the future, the new IPCC report has come up with a different way of projecting into the future. So it doesn't have representative concentration pathways like we had in the fifth assessment report. It has these shared socioeconomic pathways. What these are really are just emissions scenarios for the future. I'm not going to go through these in detail, except to say there are different pathways we can take that depend on whether we make decisions around mitigation and adaptation, about very rapidly decarbonising the atmosphere, or whether we decide to just keep going with fossil fuel development, which they call taking the highway. Or we go for something that's a bit in the middle of the road, or regional rivalry or inequality. Again, these are the sort of things you need to sit down and have a read of yourself. But for purposes of today, we'll just think about these as being one being lowest emission pathway, which is where we get rapid, the green road, if you like, and SSP 8.5 being the business as usual kind of pathway. And the 8.5 refers to what's called the effective radiative forcing of the atmosphere in watts per meter squared. So the higher the ERF, the more positive forcing, or therefore warming, of the atmosphere in the oceans. The lower the ERF, the lower the forcing. So another way to look at this is to say, well, let's go through to 2050, and let's just sort of, we're kind of here at the moment, all right? Let's look at the low emission pathway. That really only takes us to about the lower end of the Paris targets, 1.5 above pre-industrial. And there is a range, of course, because uncertainty about how quickly the atmosphere will respond to rising greenhouse gases. So we should stop doing that. The mean is the blue line, and that shows the variability around that point. And then as we work our way up to finally the 8.5 emission pathway, that would, by 2050, we would well and truly overshoot the Paris targets, which are set for the year 2100. We'd reach them by 2050. We'd exceed the 2 degrees above pre-industrial, but it could be as high as 2.5, or it could be as low as 1.5 because of the spread in the data. This also shows just how much CO2 will accumulate in the atmosphere since 1850. People say, why did you go back to 1850? And the reason is because carbon dioxide has a residence time in the atmosphere of several centuries. So once it's up there, it stays up there. So that's another reason why people say, oh, we should be blaming China and India for their emissions. Well, actually, the United States and the EU have actually put most of the emissions into the atmosphere since 1850. Not so much Australia, because we don't emit, we're only 1.5%. But of course, we have very high per capita emissions. Yes, China is emitting a lot at the moment, but historically, back in 1850, it was a peasant economy. It only really began to industrialize in the middle of, well, from about after 1949, really, when it became communist China. So all the dirty work was done previously by the wealthy countries. So that's one reason why we look at cumulative emissions rather than just annual emissions. So as we go into the future, we're looking here at relative change into the future, going on the baseline from 1850 to 1900. So that, if you like, is seen as being that kind of before you start to get the industrial effect really taking off. So going from 1950 here, you can see that global surface temperatures, we're very much dependent on what these pathways will be. So if we follow the high emission pathway, the global average could be 4.5 to 5 degrees above what it was in 1950, or sorry, relative to 1850 to 1900. That's a global average. In the Arctic, that could be as much as 12 degrees, maybe more. In the tropics, it might be around 3 degrees. Just the global average would be up to around 4.5 to 5. However, if we meet some of these lower emission targets, like the SSP 2.6, then we'll actually keep warming within 1.5 degrees above pre-industrial, which is the lower end, if you like, of the Paris Agreement. And then we have potentially somewhere between these two, we have the upper part of the Paris Agreement, which is 2 degrees. So this is all we've got to play with in the Paris Agreement. So to reach the Paris Agreement, we have to have pathways that are less than the 4.5. They've got to be these kinds of pathways. That requires significant deoxygenation of the atmosphere, rapid transition from fossil fuels, beginning immediately, not beginning in 2050. So that's pretty daunting when you look at that. What's happening in the Arctic doesn't really affect us in the wet tropics, but it's critical as a bit of a pulse of what's happening to the planet. We can see that September Arctic sea ice, this is a measure of the amount of sea ice in the Arctic in September, which is it's the end of their summer. It's the minimum time of ice extent for the Arctic. And you can see that it's now, we're reaching a point where sometime in 2050, depending on the emission pathway, it'll be practically ice-free. if not sooner. And there'll be some summers before then where it will be ice-free, but not every summer. But by 2050, it'll be pretty well every summer. But again, depends on the emissions. pH, once again, the more CO2 we put into the atmosphere, the more ocean acidification. So again, potentially, if we follow this pathway, we can start to bring the acidification, start to bring it up again into the following century, and hopefully bring it back to where it was before the Industrial Revolution. That might take several centuries. Sea level change is another thing to think about. That depends on emissions too, but the IPCC also look at these low likelihood, high impact storylines. This is really scary stuff, because what they're saying is, let's force the model not just with thermal warming of the oceans and trickling of ice melt from glaciers on the main continents. Let's actually include in there extra meltwater coming in from Greenland, and also ice shelf destabilization in West Antarctica. And when they do that, you run into this sort of low likelihood but high impact storyline. And this would see sea levels rise to well over 1.5 meters above what they are now by 2100. And even by 2050, they would be up to around 0.6 of a meter higher than now. So while that's scary stuff, it's not beyond the realms of possibility, which is one reason why they are constantly monitoring what's happening in West Antarctica, because that could lead to far more rapid non-linear change in sea level rise into the future. Another way to look at the future is to think about, I can talk about Australia here too, is to look at some spatial maps and just to look at different scenarios. So if we get 1.5 degrees of warming, this is the lower end of the Paris targets by 2100. You can see we could have significant warming in the Arctic, which is happening now. It's 2 to 3 times faster the rate of warming in the Arctic. And with the upper limit of the Paris targets of 2 degrees, it just gets worse. But we also start to see significant warming over the continents as well, and obviously the oceans, and also warming in West Antarctica here as well. This, if you like, is hothouse Earth. This is 4 degrees above global warming. I don't think there's any way we're going to get 4 degrees. I hope we don't. But we probably need to be planning for 2.7 or 3 degrees above pre-industrial by 2100. And you can see that the whole place is heating up. And it's particularly bad over the northern continents. Rainfall, we're expecting rainfall trends to follow the same patterns we've already seen in Australia. So even with 1.5 degrees of warming, we continue to get drying in the southwest of Western Australia and moderate drying in the southeast. A wetting trend over the north. This might be an advantage for North Queensland. Likewise, with 2 degrees, it just gets worse. And with 4 degrees of warming, well, we're turning places like Perth into a desert climate. Their agricultural systems will have collapsed, actually, even by this stage. With 2 degrees of warming, they're starting to get into a bit of trouble. So you can see that you get all this drying trend in these Mediterranean systems, Southern Africa, Chile, South Australia, Western Australia, but also all through the Mediterranean basin, all through this area of what is Mexico. Again, the higher the warming, the greater the trend. I won't talk about soil moisture. I haven't got time. I'll move on from that. But again, you can have a look at the IPCC report. All you can see very quickly with Australia is there are lots of areas where there's a strong drying trend for soil moisture. Okay, so these aren't very sharp, I apologise, but I just wanted to give you, before I get on to talk about the wet tropics, a quick snippet about what's in the IPCC report. And I went to the section where it summarises, if you like, what are the real big issues for the different regions. Although we're put in with New Zealand, the whole chapter is called Australasia. It does separate New Zealand from Australia because obviously the two countries have climate change. Some are the same, but some aren't. what really stands out in this IPCC report for Australia, degradation of tropical shallow coral reefs and associated biodiversity and ecosystem service value. So that stands out. That is the canary in the coal mine. All of the world's shallow tropical coral reefs are in serious trouble. The other one is loss of human and natural systems in low-lying coastal areas due to sea level rise. You might have seen something in the news about this after the IPCC report. We have so many low-lying coastal areas in Australia. We're not different to many other countries, but we are a highly coastal located society. And not only we have these human systems, but also natural systems that are vulnerable. The other one is impacts on livelihoods and incomes due to decline in agricultural production, particularly in the southwest and to some extent the south and southeast. I write about this in my book, but there are grave issues for many of our future grain crops, for rice, for cotton, and other cropping systems, for dairy. There are issues with sugarcane, so even a relatively resilient tropical crop, at some point it's going to become too hot. In particular, though, it's more those dry land or those southern agricultural systems are in real trouble. One that is relevant for Northern Australia is heat-related mortality and morbidity for people and wildlife. Most parts of, by 2080, places like Darwin and Katherine will have up to 250 days a year above 35. So you've got to question whether or not people are want to be living somewhere where it's going to be that hot for most of the year. And some days are going to be over 50 degrees in Central Australia would be quite common. The other one is not so much relevant to us in the wet tropics, but it's just lots of alpine biodiversity. But we are facing big issues with our upland flora and fauna in the wet tropics. Some of Steve Williams' work in particular, Wetmar. So that's something that I think terrain, it does need to be aware of. A lot of these are cool adapted species, and many of them are endemic species. So why are warm water corals in so much trouble? Here's the lower Paris targets, here's the upper Paris targets. This is the mean from 2006 to 2015. And this is just showing you the confidence level for transition. So when you transition, it means you change the state of your system, whether it's a natural system, a managed system like agriculture, or a human system like health systems or financial systems or whatever. And you can see this can be a low confidence level for a transition through to very high. And you can see the warm water corals, we're already in trouble. They're already in what's in the very high part of the transition. We already know they are transitioning to different states, which is why they are often referred to as the canary in the coal mine for global ecosystems. And you can see even with the lower end of the Paris targets of 1.5 degrees by 2100, you're already getting into this purple zone, and you're already looking at mass, basically bleaching being something that's going to occur initially 2 or 3 times a decade, then pretty well every year thereafter from about 2040 onwards. Once you start getting into the upper end of the Paris targets, well, it's pretty well bleaching every year. And if we get to 3 or 4 degrees, then it really means those systems are no longer going to be in the state that we remember them. They're going to be completely degraded and something else, a new kind of ecosystem. You can see that it does vary. So mangroves, you know, a little bit more tolerant. There's a medium risk of a transition once you get to the lower end of the Paris targets. And likewise, you know, you've got your low latitude fisheries, which again, that's tropical and subtropical fisheries. There's pretty high risk and for them as well. I already mentioned the Arctic. It's already experiencing, like the Great Barrier Reef, significant change. And coastal flooding, fluvial flooding, crop yields they're already under the high risk of transitioning. Some cropping systems will have to move elsewhere. They might have to move south. The wine industry in the Barossa is already purchasing land in Tasmania. So they're one sector that's way ahead of the game. You can see tourism I know in Australia it's a big risk for Northern Australia for tourism and also cropping, but also for for heat-related morbidity and mortality. And it's not just tropical in Northern Australia. The western suburbs of Sydney have nearly got to 50 degrees over the last few summers. By about 2050 onwards, it'll be regularly 50 degrees in the western suburbs of Sydney most summers. And that really will have a huge impact on heat-related morbidity and mortality. So while this is quite sobering, this is from their IPCC 2018 report. In the latest report, they unpack these in a different way. I don't think it's as clear as this original report for some reason. That's why I'm showing you this one. It is, first, where the Paris targets are, the lower and upper limit, and what is likely to happen to these range of what are very significant managed and human systems, our natural systems, for us to think about. And we think of the wet tropics, we can tick off warm water corals as being important, mangroves, fisheries, the terrestrial ecosystems, particularly in the uplands, coastal flooding, we've got some tropical cyclones, fluvial flooding from heavy rain events, crop yields, of course, on our main cropping systems, which are bananas and sugar and others, and tourism, a very important industry, and also people who live in the region and tourists, the heat-related morbidity and mortality. All of them having H's next to them, and some cases very high risk of transition. So the wet tropics, there's no real changes for what we've seen in previous reports. We still see higher temperatures in the future. We expect it to get hotter and more frequent hot days, or more heat waves. I think 2018, or was it 2019, when we had 2 days over 42 at Cairns Airport and also at the the other weather site. That was a bit of a wake-up call because it smashed the records by quite a lot. I think it was not 2018, November, I believe. More intense downpours. Cyclones are interesting. We're expecting the intensity to increase for the ones we do get, but we're expecting the frequency to fall. And that trend is already being picked up in data sets since about 1990. We're already seeing that trend in the South Pacific. Sea level will continue to rise. More frequent sea level extremes. Now, they could be exacerbated, well, they will be exacerbated by tropical cyclones and warmer and more acidic seas, but also lower oxygen content in the seas as well. How am I going for time? Hello?
Hi, Steve, this is Sarah. Yes, you are 4 minutes away from 4:30 or 3 now.
Okay, and do we then have questions?
If you have time for a couple of questions and people are willing to stay on, yeah, great.
Okay. What I might suggest people have a look at is the Australian Academy of Science. A number of people, including myself, contributed to last year, actually. Basically, the risks for 3 degrees C or more warming of Australia. So the idea being, you know, we're now being told from the IPCC report last year that it's now looking like global temperature is going to be 2.7 above pre-industrial by 2100. So the Academy of Science said, well, let's just have a look at what Australia will be like with 3 degrees more of warming. What does it mean for our ecosystems? What does it mean for agriculture? What does it mean for our coastal communities? What does it mean for human health? A whole bunch of different measures. You know, so these are just some things that I've taken from that. You know, more days above 50 in Sydney and Melbourne are very likely to be regular occurrences. So how do those places prepare for that? Number of days above 35 is projected to be 3 times greater by 2070 as compared to today in 15 towns and cities. Now, those towns and cities, that one of them includes Cairns, simply because it's in the north. So how do we prepare for that? In terms of Queensland local government areas, one study found heat waves would happen as often as 7 times a year, with events lasting 16 days on average. So what does that mean for our electricity systems when we're having to deal with the extra load at that time? What does it mean for human health? What about nature? And of course, tropical cyclones, I always like talking about them, but take-home messages there is that they will get stronger, but also their forward speed, the speed that they move across the ocean and the land, is actually declining. And this is also driven by climate change. This means that when they occur, they're more likely to sit over a place for longer, dump more rain, and cause more wind damage. So we're getting these sort of stalled events in our climate system. There's two events that have happened in recent years that are to do with stalled weather systems, and I've written on both of those for the conversation. One that's coming out this week, which is about the Southeast Queensland floods, but also the Townsville flood in 2019 was caused by a stalled or stationary weather system that hit Townsville and dumped a year's worth of rain in 5 days. So we're finding that sea level will exacerbate coastal inundation. So for places like the Wet Tropics, it's critical that everything is done to maintain the integrity of our coastlines, you know, the vegetation along our coastlines, along our streams and rivers. All those sorts of things are very worthwhile to help build resilience. And obviously being a lot more careful about any new development that might be proposed for coastal areas along the Wet Tropics coastline. This is an issue, I guess, for local governments have to grapple with as well. These more extreme rainfall events, large hailstorms, because when you've got a more unstable atmosphere, you get larger hail. So again, it's counterintuitive because you think global warming, it's still bloody cold up there, up high, and therefore you get, you know, propensity for more severe hailstorms. Not so much in the Wet Tropics. This is more of an issue for Southern Australia, and if you like, south of about Rockhampton, where you tend to get more big hailstorms. Bushfires, yes, I think we're seeing pretty strong evidence that they're going to increase. And they're saying that they could increase by 30% or more in southeastern Australia, the fire risk, if we reach 3 degrees or more of warming. And greater changes in seasonal rainfall in southern Australia. Northern Australia, though, overall, rainfall trends are not projected to change very much at all. Annual rainfall is going to be much the same. Wet seasons will still be wet seasons. Yes, they'll vary from wet season to wet season because of El Niños and La Niñas, but we should basically, compared to other parts of Australia, the Wet Tropics and Northern Australia generally is not so threatened by less rainfall, just more heavy rainfall events, but total rainfall shouldn't change too much at all. There'll still be the dry season and the wet season. And there might even be an increase in rainfall in some parts of Northern Australia, as we've seen already from that trend. So maybe people might move north. However, the heat might be something that will put people off. Trade-off is that it's going to get hotter as well and higher evaporation. So there might be certain triggers there that make certain cropping systems difficult. I'll still shake my head when I read the plans for developing Northern Australia for broadacre agriculture that doesn't really look at this climate projections and realise that a lot of these things are going to fail. They're going to fail badly, some of these schemes. You know, when you're getting into areas that are going to be so much hotter, not so much the coastal areas of northeast Queensland. I'm talking more about these proposed development areas across other parts of Northern Australia. I really question how they're going to be able to have cropping systems and how they're going to get people to go and live there. But that's another story. I won't talk about cyclones because I'll run out of time. So I'll stop there and we'll come back to the chat.
Thanks, Steve. That was incredibly informative. We have one question so far in the chat from Stuart at Terrain, and I can read it out to you, or if you want to read it yourself to us, whichever's better.
You read it out, and that way everybody hears.
Okay, so he's asked whether you provided forecasts looking forward to 2050 and 2100, but many of us are involved in planning for shorter time frames. How do you advise that we start using this data to plan for the next 5 years or so whilst keeping an eye on the future?
Okay, I think it's a good point. First point is that we've already been living in climate change, certainly quite strongly for the last 20 years. So we already have an appetite for what's happening out there. And I think what we can do is look at these long-term projections and say, well, all right, we're pretty certain that rainfall isn't going to change very much. But what we are pretty certain, though, that when we do get certain events like cyclones and even monsoon activity without necessarily having a cyclone with it, because there's going to be so much more heat in the atmosphere and the oceans, we're just going to get greater volumes of water falling on the landscape. So we've got to prepare for those stronger fluvial floods and flash floods. It's not just in the north, it's already happening right down here into the subtropics, as you've seen. So we need to prepare for that. And again, sometimes it might just be just good, solid NRM practice like we're doing at the moment, doing everything we can to conserve our soil, our waterway health, and buffering our river systems and so on. So a lot of things we're doing at the moment are kind of no regrets things, kind of keep doing a lot of those things. But for 5 years, the climate's not going to change very greatly, but it will be important for things like long-term infrastructure, because when you build infrastructure, you're building it for a century sometimes or 50 years. So therefore, you've got to think about that longer time frame. That's probably not something that terrain does, but its partners do. Agriculture's been adapting to climate change for many decades now, particularly in parts of Australia that have had significant drying, like in the southwest. They're already changing their practice to meet that. And I imagine it's the same with our farmers, who are also, dealing with very high variability. And one of the things about the wet tropics, one of the reasons there's no signal in our rainfall is our interannual variability is just too great. Too much, it's too great from year to year. However, one signal that is strong for the wet tropics, as it is for the whole planet, is we're getting warmer. So because we're getting warmer, the days are getting warmer and the nights are getting warmer, that is going to start to impact on, well, it is impacting on our ecosystems. We're already seeing the effects in the uplands. And we expect it also to impact on agriculture and sugar, for example, with warmer nights, and potentially more, thinking about biosecurity threats, but also human health. There's another issue for our communities to be thinking about too. People did die in Cairns in that heat wave in 2018. Because it blew the record by 5 degrees. It was such a big record that a lot of people were caught out. A lot of older people were caught out by that. I'm not sure of the actual figures, but there were some people who died because of heat stress, along with our flying foxes, of course, the fruit bats. Yeah. So I think it's a matter of, if you're going to, the answer to that question is we should be keeping our eye on what those projections are saying, that group I just showed you, and what are some of the things we've already been seeing happening, and we should be adapting our systems to deal with that. And also looking for opportunities. What opportunities can we have for climate change in the wet tropics? We know we're going to have plenty of water in the future. Other places may not have that. So that's an opportunity. What can we do with that? So that's another thing to be thinking about.
That's a lot to think about, Steve. Thank you for that answer. There's a lot in it. There was another question from Wayne Young at Gulf Savannah NRM, who asked about where we're currently tracking in our CO2 emissions. He saw some research last year that showed we were currently tracking beyond SSP 5 to 8.5. Is that correct?
Yeah, and Wayne's correct, yes. Unfortunately, we still have a long way to go to meet those Paris targets and even the mid-range targets. Australia now has agreed to net zero emissions by 2050, bipartisan support for that. However, our mid-range 2030 targets are pretty abysmal compared to other wealthy countries. We're currently 26 to 28%. We should be aiming for more like 54%. 46 to 52% is what we should be aiming for. So we're still waiting. It's a bit like hearing crickets there, still waiting to hear that, for some action on that. Now, it may well be we reach those targets because of what the states and territories are doing, but still it needs to come from that national level. That leadership needs to be shown at the national level. But at the moment, globally, we've got a long way to go to start to bring those figures down, as Wayne has suggested.
Another very cheerful bit of news, Steve, thank you. So another question from Geraldine Maguire was, do you think that the vegetation systems in the wet tropics have any adaptive mechanisms to cope with future climate change?
Well, I know there are some studies where they're trying to answer some of those fundamental questions. So particularly with the plants, so they're able to take some of these upland, this is James Cook work, take some of these upland plants and try growing them down at sea level and growing them under different CO2 conditions and temperature conditions. So to work out their plasticity, if you like. Mm-hmm. And so the answer is yes, I'm pretty sure there is plasticity is high for some and not for others. It's a bit harder to do experiments with animals. You can't sort of bring a rare animal down and start sticking, heating it up. See you, Jeff. But there has been some work done with upland, with Andrew Krockenberger, looking at upland, some of the green ringtail possums, and in particular the ones that are more vulnerable to temperature, the lemurids, and they really can't cope with the heat at all. So for animals, it may not be the gradual change in temperature; it might actually be the heat waves that are the tipping points. Whereas for plants, it might be quite different. Their physiology is quite different. So the answer is yes, I do believe there's plasticity. It'll vary from species to species, but I also believe the animals probably have their plasticity will be lower, especially if they're cool adapted upland vertebrates. May have much lower ability to handle those heat wave events in the future.
Yep. Thank you. We do have a couple more questions. If people want to hang on to listen to Stephen, if he's got a couple more minutes to answer them. But before that, I just wanted to thank everyone for joining us today, and we'll keep you posted about future events. I'm hoping to have Steve back on to do some more as well. But Steve, if you can hang on, I can ask you a couple more questions, but I just wanted to thank you for your presentation already today.
No worries.
Because I noticed people are starting to drop off. Yeah, there was a question, there's a couple about sugarcane and banana. Lisa from Mulgrave Lane has asked about when you think the effects on sugarcane will kick in. I guess it depends on the scenario, but that current scenario you provided before is not very positive.
Yeah, look, I have actually read some of this as part of one of the chapters in my book, looking at that sugar industry, and I can't speak for bananas, sorry. Bananas are currently grown in equatorial countries, in Africa and so on, but they're kind of growing with a bit of elevation, which will obviously compensate for the temperature to some extent. So, large parts of East Africa where they grow bananas, in Uganda, where I think a lot of bananas come from, they're grown at 600, 800 meters above sea level. So there's an elevation effect, even though they're right on the equator. Look, I suspect with sugarcane, the issues might be around temperature and sugar levels, requirement for cooler nights. So they are a pretty robust crop. They handle cyclones, they handle flooding. The reason they're grown in the wet sugar is grown in the wet tropics is because it has that resilience. It can handle odd droughts as well. I think sugar's biggest problem might be in places where it's irrigated, where there might be lack of water. Because water resources will become tighter. So there might be an issue there, but it might be CCS level. It might basically be sugar content issues might be the main driver. But at some point there'll be an upper limit where your productivity will start to come down, and also pests become more of a problem. So all those things that come with a warmer world are going to actually affect most crops, and tropical crops are no different. And many tropical crops are already grown pretty close to their top of their thermal range anyway. So they don't have a lot of space to play with, except that maybe you can move south. You can start growing sugar further south. So go south of Grafton or or whatever. But then there'll be other factors that come into play, like day length and so on. Same with bananas, you know, you just move south if it gets too hot. And then water becomes an issue. So it's a complex thing, but I think both industries are pretty engaged in climate change and adaptation and developing new varietals and doing lots of very interesting work and they know a lot more about it than I do. I'm only chipping around the edges.
Thank you anyway for that, Steve. That was fantastic. That's the last of the questions on the chat. So I think we can give you a leave pass now. You've given us plenty of your time today, and so has everyone else who's hung on at the end. Everyone's really appreciated it from all the comments I can see. So I'll certainly be in touch about some more webinars in the next few months if you're keen to share more chapters of your book. No
problem. We'll do something on adaptation. How's that next time?
That would be cheerful, because this was sobering, but I hope was also inspiring for people to take action sooner rather than later. Thank you.
Thanks, everybody, and I'll catch up soon. Thank you.
Thanks, Steve.
All good. See you later.
Thanks, Steve.
Yeah, thank you. Cheers.